Well, this is just kind of a teaser for later. This is actually from a shot of Trinity Test. We're going to talk about what this is all about after a bit. So I'm going to start off with a little talk about sort of unit analysis, if you will. Let's see. Oh, I don't need my camera. Okay, so let me kind of adjust this too. If I can find it. Well, welcome to Math Club. And so this is a very, this is a talk that in a certain sense is very elementary, right? Everybody's done unit analysis, right? I mean, from way back when, you may have even had exercises in like grade school or wherever in Tennessee, high school for sure, where you turn things like Fahrenheit into Celsius, and things of this nature, right? So what do? You do the comparisons of units. And there's a, for example, a formula that takes Fahrenheit to Celsius. But there are many equations from physics, chemistry, and whatnot. So here's some famous ones, right? Einstein's famous one. Got to give a shout out to Newton. Force is mass times acceleration. Kinetic energy. Kinetic energy is this. Or potential is this. You might know what that one is. Yes, the ideal gas law, right? Have you ever noticed these equations or these physical equations often turn out to be polynomials, right? There are some others that have fractional exponents, but they're almost always a product of monomials. If I use the term monomial loosely to include not just integer powers, but in fact, rational number powers, right? So why so many polynomial-like equations? So, I mean, have you ever wondered why Newton just didn't say this? Right? Why is it not F equals mass times E to the acceleration, right? I think we get a little bit stretched in that universe, but why does it not work out this way? Or why is it not F equals M times sine of the acceleration, right? And the big thing is because of units. Right? So force is sort of a made-up quantity that really, I mean, it exists out there and it's very practical. What is it? It is a mass times an acceleration. Now, what is this allowed to do? Well, suppose you measure force or any other of these quantities in two different unit systems. Right? I mean, you could certainly, what's the use? So the standard unit of force in the metric system is newtons, and in the English system it is pounds, right? And the unit of mass in English is just odd. Isn't like one of them a slug or something like that? It's just, it's awful, right? But sometimes you want to move from one unit to another. The metric system, I mean, you gotta love Americans. What makes America the greatest country in the world is we can stand in the face of something as logical as the metric system and say, no. But I can't, but really, it's also what you grew up with, right? Because I mean, if I have to think about temperature in Celsius, I have to think about it a little bit, right? Where my wife, who grew up in a system that was metric, I mean, Celsius is very natural to her. But when she's, oh, it's hot, it's 35 Celsius, I have to think about that for a moment, right? If you want to move from one unit system to another, if you're in pounds, your force is going to be much different than newtons, right? You're going to get a different number. But what should be preserved, right? Twice as much force should be twice as much force in any unit system, right? So let's see what happens. So suppose we have two forces. In two unit systems. Right? So you have F1 is M1A1, and you have F2 is M2A2. Now, if you're in the metric system, that's going to give you two numbers for two forces. But let's suppose that you also have this in another system, right? So you've got to convert your mass to whatever the conversion is in the other system. You've got to convert your acceleration there. So let's say that M1 goes to, let's say, alpha M1 over here, and well, let's say in general that a mass goes to alpha times the mass over here, so you've got a constant, and we have acceleration goes to beta, say over here. What happens in this equation is, in the new system of units, this becomes, well, that's scaled up by alpha, that's scaled up by beta, and same here. And so the ratios are preserved, right? So the relative measure is the same. If the force we feel here is twice as strong as this force, that's the same in the other unit system. It's twice as strong as force. And this is what you want. Now, I did a very simple example where the M and the A were both, of degree 1. But it's easy to check that if you scale in any unit system, as long as you have polynomials with rational exponents, then this will preserve what you want to preserve, right? So this is one of the reasons that we don't have this right here, because what happens if we have M e to the A, right? Well, at the first unit system, and F2 is 2, A2. When you do your conversion, the new force here becomes alpha M1 e to the beta A1, and F2 becomes alpha M2 e to the beta A2. And now the ratio is, there's an exponential factor, right? I mean, this is a game changer, right? So this is kind of a big justification. There are actually theorems and what kind of functions that you can have these unit physics things in, and basically it turns out to be monomials. And this is a reason why these formulas are all like this, because basically you're chasing units. Of course, some things are unitless. Let me also point out, here's another way to look at Here's another way to look at the problem of the exponential. So this is kind of a practical way to look at the problem of the exponential cost. What's the units of, what are the units of acceleration? Right. So let me say length per time squared, right? Well, right. If you look at the power series expansion of this, you see you've got a mismatch problem with your units here. Right? It's interesting. So ask yourself this in conjunction. This is another reason why polynomial, or more generally, rational powers of your variable work very well in the situation of units is, can you do this power series trick there? Well, suppose instead of e to the a, you had a to some power, right? What's the power series expansion of, say, x? What's the power series expansion of like a to the n about 0? Well, it's just a to the n, right? If n is a positive integer, right? If n is a negative integer, then you don't really have a power series expansion about 0 anymore, right? And if it's fractional power, you've got the same thing. Like if you take the square root function, you can't expand that about 0 because you've got a problem with, eventually you have a problem with derivatives at the origin, right? So it's all coming together. So there are some constants that show up in physics and in math that are unitless. Well, they're just like a pure number, right? Can anybody name this constants used? Unitless.
The Planck constant, is that one?
No, that actually does have a unit. I actually gather, yes.
Is gravitational acceleration unitless?
No, the gravitational constant of the universe is got units to it. One that jumps up to me is, and in fact, if you want something unitless, it's often good to take a ratio. I just invented this notation. I don't know if this is going to get mad at me for this, but this is the ratio of rest mass of proton to, so it's a ratio that one's unitless. And actually, that is a fixed ratio. I mean, I haven't really counted all the protons in the universe, the electrons. Although there are some crazy quantum mechanics people say maybe there's only one, as a matter of fact. But let's not get too crazy in this. If you look at this ratio, there's a lot of physics behind that. If you change that ratio, right? How many of you have ever seen did you ever watch Star Trek: The Next Generation? Being old, right? Anyway, there's this kind of godlike creature that comes and bothers Captain Picard all the time, named Q, and he got turned into like a moral, and he was all in trouble. And they were trying to get him to solve a problem because of all his wisdom. And he says, "Oh, that's easy. Just change the gravitational constant of the universe, right?" Which I guess some people can do. If you change this ratio, it will change physics quite a bit, right? Depending on how you change it. So this unitless constant is something that's very important to us. Some other examples are pH, and that's from chemistry, specific gravity. But, and again, what I'm doing is I'm taking a lot of advantage of ratios here, right? So these are kind of ratio things. For one that's not physics, how about lots of people are watching baseball now. Winning percentage is a unitless constant, right? If you take a ratio of games won, games played, or whatever. Define structure constant. The reason for this actually has something to do with. This apparently puzzles physicists about why it's out this way. E squared over 2 epsilon 0, the Planck constant of speed of light. So this is the Planck constant, this is speed of light. This is called the electric constant, and it basically quantifies the strength of various electromagnetic interactions between elementary particles. And this, the E on top, is the elementary charge squared. This is approximately 1 over 137 and a little bit more. Right. This is a fundamental constant of the universe that's actually unitless, right? But yes.
And what default value does epsilon have? I thought it was just like an arbitrarily small value.
No. This is actually a defined physical constant. Right. This is, and I don't know what it is. I have to look it up. But we can do that at the top if you like.
And all those symbols in that have units, they just all cancel.
That's correct. All the symbols have units and they cancel out, right? So we actually know there's one for math. So I've paid my respects to chemistry, physics, and even basketball, but there's actually a constant that comes up through a unitless measurement in math. There you go, pi. E does as well. But pi, because by definition, pi is the circumference of a circle divided by its diameter. And that's probably one of our most famous sort of unitless constants here. Also, radian measure in general is unitless, right? Because what is radian measure, right? You have basically a circle and you measure a distance divided by the radius of that particular circle. So it's unitless, right? By the way, here's a very fundamental, this is one of the things that's really kind of sexy about math, and it kind of makes you angry too, right? Here is a fundamental question. And I'm going to use it to segue into something else. Those are supposed to be concentric circles. Let's suppose that these are beautifully drawn, I might say, concentric circles here. Here's my question. Does anybody know if you have a circular sector? Does anybody remember what this distance here is? Suppose that this distance here is R. What is this distance here?
They are.
Yeah. Theta times R. Again, this is unitless because it's a radian measure. Theta times R, so this is the length here. And this doesn't depend on R, right? Doesn't matter what R is, it's always theta R, right? Prove it. Right? It's obvious, right? But it's not. Anybody know how you prove this?
I mean, if I'm just waving my hands in front of my class, I tell them, like, look, go all the way around, it's 2 pi r.
that is a beautifully circular argument. A circular argument. Yeah. So, do you know how pi is actually sort of derived from this perspective? Is what do? You take the circle and you divide it up into a bunch of smaller triangles, and you sort of make the triangle smaller and smaller, and it limits to pi, correct? So you don't really need limits to show that these ratios are the same. All you need to do is know that that process is there, And if you do the process, it is independent of the radius because of similar triangles, right? The problem here is we've got like an arc here, but if you do the exhaustion here and you do it here, you will see that the pieces that you get going into the limit are the same pieces. So if there's an answer here, which there has to be, then it has to be the same as the answer here, right? I don't know an easier way to do that. I don't know a quick way to do that. It depends on similar triangles, whatever. But we're going to take that as written that this is that actually so pi is just what this limit is, and of course what we really argued here is that pi does not depend on what r is. It doesn't matter what your r is, you always get the same value in pi. And see, that's kind of a fundamental thing we've all already taken for granted, but when you think about it a little bit, it's not 100% clear, right? So here is kind of, how many of you have had Calc 2? How many of you are teaching Calc 2? So here's like, this is like a very small thing, but I'd like to point this out. So here's one application of units. So suppose I'm teaching this on the interval from A to B. I haven't taught Calc 2 in a long time. I do remember it's basically disintegrating the function, and there's also something to do with the length of the interval. And what was it, B minus A over 2, or was it 1 over? Okay, yeah, gosh, I don't quite remember, and all my sweaty students are looking at me, and I'm up here shaking. But how can I figure it out if I don't quite remember?
Give yourself a constant function.
Actually, that's a great answer, right? Do it with a constant function and see what works, right? That's a great answer. But another answer is this, units. So y has some units u, and x has, let's say, the same units, right? Length, if you like, right? What's the units of this integral? It's length squared. Now the average value of the function should have the same as the function, right? And so it has to be that. You're going to have a length in the bottom to make the units behave correctly. And this is average value of a function, which is a pretty abstract thing. But if I sort of force units into that by thinking of f of x being a length and x being a length, then all of a sudden it makes it kind of come together for me. And of course, there are many times, especially in Calc 3, when you get these surface intervals and stuff, I have used this for a gut check many times by looking at the interval. Another one, I don't know if the Calc 2 here does it, but do you do the applications like force due to hydrostatic pressure and things like that? If you do that, paying attention to units is incredibly useful, right? Because especially with those kind of problems where they have like the water behind the dam and what's the force due to hydrostatic pressure on this, there is no formula. You really have to build it, right? And if you remember units, then everything is much easier to implement. Here is another application, if you will. What is the circumference of the Earth? This is one of my favorite. Way back when people with nothing but goats and sticks were able to figure out amazing things, right? You know, it's amazing. This actually took place in maybe ancient Egypt, perhaps. I don't know how many of you heard the story, but there was a well, I was gonna say a mathematician, but probably really somebody that you would call a natural philosopher. Because back then, those people did everything, right? They did math, they did physics, they tried to make gold with Isaac Newton, witch's hair, things like this. So they were kind of all over the place. And this guy wanted to know what the circumference of the earth is. And that little statement there, I'll probably get my video on YouTube. Thumbs down to my Flat Earth Society out there, but we'll power through that. What happened is I'm going to draw the Earth here. So it's got some large radius, and of course, to find the circumference, all I got to do is find the radius, right? But this is way back when people didn't know. But what was noticed was this person who was, and I think actually they called him whatever the word is. I think they used to call him Beta because they said this guy was the second best at everything in the world, right? Which I think is a pretty enviable title. But anyway, he lived in a town where yeah, I guess he lived right here. He lived in a town, and he heard about this other town that was south of him, where there was a well in the middle of the town that at noon on summer solstice or whatever, the sun shone straight down the well. So it's coming straight down. But he also knew that this was not the case. You couldn't see all the way down the well in his town at the same day. So what he did was he had a stick, probably not quite that high proportionally, but I draw it there so we can see it. Right? And he noticed that on that day, it casts a shadow of length S. Okay. And he also knew that the sun's coming straight down here because you can see down the well. Now, we'll make a couple of assumptions here that are reasonable assumptions. The Earth is not flat, but it's locally flat, so we will assume that this is almost a perfect triangle here, with the L being the hypotenuse, and this being a 90-degree angle. So the sunlight is, we also assume the sun is so far away that the beams of light are parallel, right? So this angle here is also theta, correct? Because it's basically two parallel lines, sunlight cut by a transverse, right? And he knows enough about circles to know this formula that we have here, right? So this distance here along the curved route here is equal to theta times the radius of the Earth, which he doesn't know. But he also has another trick because he knows that if you look, you have this right here, I guess S over L is equal to the sine of theta. Right? So he knows what theta is. In fact, theta is equal to the inverse sine of S over L. So in particular, what this dude now knows is R is equal to B over whatever this theta is, inverse sine of S over L. Correct. And so now he knows everything because he himself can measure the S and he knows how long his stick is. So he's got that going on for him. The only thing he's missing is what B is. So he actually paid a guy to pace it off. All right. Which, you know, I mean, it's a bargain, right? It's not like he had to go across Antarctica or anything. So he paced it off. He filled in D. Measured this distance Now he's got everything. Now he's got the radius of the Earth. And once he's got the radius of the Earth, all he needs is a 2 pi, and he's got the circumference. And this calculation was performed with sticks and wells and a guy walking like thousands of years ago, and they got it to an amazing degree of accuracy, right? That's what I dig with the human brain. But again, this depends on, among other things, that wholly, which means that, you know, that pi is a unitless constant here. Okay. Any questions so far? Okay, so now,
Actually, I have.
yeah,
With the circle. If you were to change the underlying geometry to like hyperbolic geometry, that equation changes. I think that like, so if you had a hyperbolic sheet and you drew a circle on,
Mhm.
so all the points equidistant from a singular point. As that radius gets bigger and bigger, the circumference of the circle grows exponentially.
right, but then maybe the well wouldn't hold water in, so yeah. Yeah, I mean, we are, of course, restricting down to this geometry. And of course, actually, and this is another good thing about approximations, because his distance was probably reasonably accurate. I mean, if the guy was good at counting and pacing off, but of course, you know, there's not only the error in measurement, but even if you can somehow measure this perfectly, this is also curved, right? So this isn't honest to goodness a triangle, but it's close enough for rock and roll. Right? So now let's kind of focus on the centerpiece. And first, I want to have kind of a thought experiment. So I want to put this up for you all out there to see too. Let's see if I can do it right. Oh, okay, I was gonna say, I'm gonna open Trinity. I want it bigger. Okay, so. So let me go through my story here. There we go. So hopefully everybody can see that except for us. So they did the Trinity test. The Trinity test was the first A-bomb test. And of course, you know, the Manhattan Project, they were trying to build this bomb, of course. And of course, we did our naughtiness with the bomb and took care of things. But in about 1947, you know, the US government started releasing some of these movies and pictures of the bomb. And I'm sure it was a Cold War thing. We want to scare the Soviets. And there was a lot of that kind of back and forth that went on in the 50s and 60s. At the time, the kiloton yield of the atomic bomb was classified information. They would not say how much energy this thing is putting out. It was a big secret. But of course, they wanted to intimidate our Russian friends. And so they had these movies out, and they actually had, you can't quite see it here, but there's a scale here. It's about like this. It says 100 meters. This is a screen capture from the movie, and they circulated this. Well, it is 6/1000ths of a second after detonation of the bomb, and it's looking at a radius of about 80 meters already, right? Now, how much energy that is, again, classified, but Jeffrey Taylor, I think it was, actually figured this out to a great degree of accuracy. So how do we do this? How are we going to figure out what the yield of that bomb is? Well, the first thing that one would want to do is figure out what some of the players are going to be. And this is really this is kind of the clever part. Well, it's just part of the clever part of doing this. So your goal, so my goal is on the still discover the secret. I want to know what the energy is. Energy. The question is, what variables should I consider? What do you think are relevant? And of course, it's also important to say, can I limit myself to what I might be able to glean from this picture or from other sources of information, stuff that's not secret?
Propagation.
Okay, so what you mean is,
Like how fast, like if you have a whole bunch of energy all in one place, how fast is it going to scatter?
okay, let me simplify what I think you're saying. The radius of the,
Yeah,
we're gonna make two key assumptions here. Number one is we're gonna assume this started from a small space, okay? So supposedly that is, it's whatever the active material is inside the bomb. And like any good physicist, we're going to assume it's point mass, right? So it starts right from there. And we're going to assume that the shock wave is a sphere, right? Looks like it's a pretty good assumption here, reasonably. And of course, as the shock wave goes out, it'll probably lose a little bit of that. And also, it was detonated off the ground, right? And so, of course, it loses some of the sphere part as soon as it hits the ground. But we're going to make that assumption. It starts at a point and it expands in a sphere. And we're going to assume that none of this is corrupted here, or close to none of it's corrupted. So the other variable is R, radius of shock wave. What else?
atmospheric pressure.
Okay, you're close to that. Time, right? For sure, we'll throw in time.
There's a Southwest standard. How do you use that?
We're going to also use right. I mean, if I explode an atomic bomb in the air as opposed to a giant pool of maple syrup, it's probably going to be different as far as the shock wave goes, right? So we're going to use these players here. Now, let's look at units, right? So let M mass, L equal length, and T time. That one's pretty much uncorrupted, yes. So what are the units? Energy. Right? I mean, I have to think about this, but I always seem to remember from high school that kinetic energy thing was 1/2 mv squared, right? So energy has a mass and velocity, so it should be v squared. So velocity is length per time, right? This is how fast you travel. So this should be length squared over time squared. That should be the units there, correct? Units of time are time, right? And what else do we need to collect here? And the units of the radius is what I'm calling L, right? Just the length of the radius. And finally, how about rho, the density of the medium? So density is right, it's like a mass divided by, in this case, volume, right? So the density of the medium, which is air in this case, should be M over L cubed. Right? And so what I'm going to do is, so I've got pictures, and my pictures are basically expressing the radius, right? I didn't put the other picture up, but there's another one that's kind of a prettier picture, if you like nuclear weapons. That's a little bit further, it's like at 0.016 seconds, right? These things are, the pictures are expressing radius as time goes on, and it should depend on these other variables as well. So we'll assume that the radius, well, more or less, is, let's say, what are my relevant variables here? Right, is energy to the x power and t to the y power and rho to the z power. And we'll tack on a constant, right? Now, it turns out that this constant, what's his name, Taylor actually had some evidence that this was actually very close to 1, which is convenient, right? But this unit analysis allows us to now do the following. And guess what? For those of you that are in one of my classes, we're going to have some 1-year algebra, right? So let's compare units. So first equation, length. On the right side of this equation, this is just R, that's 1 unit of length. This is, E is M, what was E? It was ML squared, 2 squared. Right, so when I take the x power of this, it should be m to the x, L to the 2x, t to the minus 2x, right? And it should be just straight up t to the y, because time is time, and it should be rho to the z, so that's going to be m to the z, and L to the minus 3, right? And R is just L over 1, so just compare. We'll see. So unit wise, 1 should equal 2x minus 3z. Correct? What's next? How about M? Compare M. There's no mass on this side. And so that means all the masses on this side have to cancel out. So we have x plus z. That has to be 0. And 3 time. And again, on this side of the equation, there is no time. And so the time's got to be gone. So I get minus 2x plus y. Must be 0. Agree? The first equation here, this essentially means that z and x are just opposite in sign. So this equation means that 1 is equal to 5x. So x is equal to 1/5. Z is minus 1/5. And let's see, y is 2/5. That's what units by here. So this equation now becomes R is equal to K times e to the 1/5. That's capital E, of course. Energy to the 1/5. Z, where does Z go? Rho to the minus 1/5. And I guess it must be time to the 2/5. Everybody okay with me? So this basically gives us an equation for R in terms of these other 3 variables, right? This is a reasonable thing to do. K was approximately 1. In fact, it's a pretty good approximation of 1. This allows me to get, of course, energy in terms of the other things. Well, the energy is now R to the fifth times rho over T squared. And there is your equation for energy. And this is everything we need to know, because in fact, I'm only going to use one of these snapshots, because at 6/1000 seconds, R was approximately 80 meters. Right? You can't see the scale on this, but 100 is about like that. So your radius is roughly 80 meters. And there's other of these snapshots. And with other of the snapshots, depending, they all kind of bounce around. They all kind of demonstrate that this is a really, really good approximation for a short period of time, right? And the rho is something that's known, because you could just go to like a chemistry physics book or whatever and look up the density of air, maybe in New Mexico or whatever, is 1.2 kilograms per cubic meter. I think is the figure that they used. And so this comes out to, so I just get rid of this now. So if you just plug and chug now with these figures that we have, we get, so plug in these values here, we get energy is roughly, what did we get? About 1.1 times 10 to the 14 joules. And 1 joule is, you've probably never seen this unit conversion yet, so don't ever say I never gave you anything. This is 2.39 times 10 to the minus 13 kilotons of TNT. That's not a unit that you run across every day, but 1 joule is about that. So if you transfer this unit of joules into, notice this is close, so it's going to be, you know, some kind of small number. I got about 26.1 kilotons of TNT. That would have been the yield of that bomb. And this is classified information. According to Wikipedia, the real measure of what they had at that bomb was 24.8 plus or minus 2 kilotons TNT. So not too bad, right? We're just looking at one snapshot from a movie and doing nothing but analyzing units, right? And that's what you get, right? So this is yet another reason why I love mathematical science. Okay, any questions on that? Let's see if I've got any chat questions here. Oh, so Aditha says epsilon sub 0 is a permissivity constant related to the strength of electrostatic forces. Okay. And oh yeah, there's another somebody else offered, there's lots of beautiful constants. Somebody else offered index per fraction. All right. Any questions? Questions? All right. Well, next week, Sean's going to be talking. So hang on to your hats for that. And other than that, you guys have a good weekend. Eat all the pizza, steal it, and the Cokes if you haven't already. So have a good one. We'll catch you all next time. Bye, y'all.